Welcome to Differential Equations podcast. So we're going to be solving some more differential equations here. So step one, we want to isolate the x terms on one side, isolate the y terms on the other side, isolate y on the left, dy, and x on the right, dx. Because we can move dx to the right, but we can't really do anything with dy. All right, so first of all, I'm going to do something with this equation. I'm going to leave the dy dx as it is so far. So we have square root, actually I'm going to rewrite that as x to the 1/2 dy dx. If you notice here, I have x's and y's in an exponent. But if you remember the product rule, so when we multiply like bases raised to a power, we add the exponents. E to the 5y plus the square root of x is the same thing as e to the 5y times e to x to the 1/2 power. All right, so now you see I've got it as a product with x's and y's, and so now I can divide to move one to the other side. I am going to have to move the y term over and the e to the 5y to the other side because dy is over there. So let's divide both sides by e to the 5y. So I did in one step, I used the product rule and I wrote the square root as an exponent. So I'm going to change the change reciprocal to negative exponent. I'll do that in a moment because I haven't moved the term yet. So I'm just dividing both sides by e to the 5y. All right, so now I've got 1 over. So 1 over e to the 5y, x to the 1/2, dy, oh that looks like times. Let me fix that exponent on x there. X to the 1/2, dy dx equals e to the x to the 1/2. All right, so now we've moved that over. Let's do the same thing. We'll divide by x to the 1/2. And then we'll multiply both sides by dy. So we have, we'll divide this side by x to the 1/2. And maybe at the same time, we'll multiply by dx. Okay, squeeze that in here. All right, so there we have it over on that side. I'm going to divide, oops, not, yeah, x to the 1/2, that's right. X to the 1/2, that's the one that's moving. And then multiply by dx. All right, so over here, dx's are going to cancel, right? And x to the 1/2 is going to cancel. So now I have on one side, I have 1 over e to the 5y dy equals, and then I have e x to the 1/2 x to the 1/2. All right, let's rewrite the e to the 1 over e to the 5y as e to the negative 5y dy. Sorry, that looks like an 8. Equals e times x to the 1/2 divided by x to the 1/2. And now dx, somewhere that dx got lost. And now we can integrate both sides, and we can solve. We have to do u to u substitution on the right-hand side. Let me see if I have space on the next page. If I save some space. Yeah, I did. All right, so I'm going to continue this problem on the next page because I am running out of space here. So I have e to the negative 5y dy, and then e to x to the 1/2. Okay. So we have e to the negative 5y dy equals, and then we have e to the x to the 1/2 over x to the 1/2 dx. All right, so if the u is x to the 1/2, then the du would be x 1/2 x to the negative 1/2 dx. So the only thing we don't have is we don't have the 1/2 part. So you see our u is going to be that exponent on e, because that would be a chain rule, and we have the other part of the chain there. So when you have, if you think about it, what if I take the derivative of x to the 1/2? Oh, that's what's going to give me an x to the 1/2 in the denominator, because that's x to the negative 1/2. So we need to multiply both sides by 2, and then we can do a substitution there. So on this side, we've got the substitution as 2, and then we have e to the u du. Right? So the u is the x to the 1/2. The 2 du is the x to the 1/2 dx in the denominator there. All right, we need another substitution because I don't just have an x or a y on e on the other side either. So I'm going to call this a w dw substitution. I don't want to call it u because I already said u is x to the 1/2. I can't go saying u is something else. So w is going to be negative 5y. So on the other side, we're going to have e to the w power dw. Now, I don't have the only thing I don't have, when I take the derivative of negative 5y on the chain, I don't have the negative 5 part. So we're going to have to divide both sides by negative 1/5, because there must have been a negative 1/5 to cancel out the negative 5. That's how we know there's a negative 1/5. So the 2 on the right-hand side canceled out the 1/2 that should be there. And the negative 1/5 on the left side canceled out the negative 5 that should be there on the chain. All right, now I can just integrate, no problem. So now I've got negative 1/5 e to the w equals 2 e to the u. I'm going to put the c on this side. I'm going to substitute back. So I'm going to have negative 1/5. And you can put 2 c's and then combine them later. That really shows that you know that, hey, each time you're going to have a c. I did just kind of save a little bit of time. Just put the 1 c there because that's what's going to end up happening. So negative 1/5 e to the w is negative 5y. Okay. Equals 2e to the x, 2e to the x to the 1/2, and then plus c. Again, I'm going to solve for c here. It's impossible to solve the equation in terms of x or y, so let's just solve for c instead. If I didn't have 2 of them here, then I'd be okay. So let's just move everybody over. I'm going to move the negative 1/5. I'm going to put the c over here. The sign doesn't matter, right? It's just some constant. Some constant is going to be equal to 2e x to the 1/2 plus 1/5 e to the negative 5y, right? So that's the equation who has that up there as its differential equation. Okay? So we'll finish this one. Right, let's see how many more differential equations I have. All right, so now we want to isolate the x terms on one side, isolate the y terms on the other side. It's going to be another one where, if you notice the bottom step there, we're going to be solving for c. All right, so I'm going to multiply both sides by y, all right, and I'm going to multiply both sides by dx. So I'm going to write over here. So I've got dx times dy dx. And actually, let's put a y over here too. Y dx dy dx is equal to x, y, and y dx. All right, so all we're allowed to do is add, multiply, and divide. You can't add or subtract anything. All right, when we multiply and divide both sides by y and dx, on this side, the y's will cancel. I've got x with dx. This is a fairly simple integration here because we've got y dy equals x dx. We'll integrate both sides. All right, so this is going to be y squared divided by 2 equals x squared divided by 2 and plus c. I got to put the c somewhere, or I can put 2 c's. I'm going to solve for c. All right, so I'm going to move the c over and the y over, and I'm going to also multiply everything by 2. All right, so we'll just multiply everybody by 2. Just get rid of those 1/2 because that's not really needed. So now we've got y squared equals x squared plus c. All right, just multiply both sides, everything by 2. Okay, so multiply everything by 2, but 2 times c is just still c, because it just means constant. If I multiply a constant by 2, I still have a constant, right? I don't have anything else but a constant. So I'm just going to move, the c over here, and I'm going to make it c equals x squared minus y squared. Someone had to be the negative. May as well go alphabetical. All right, here you cannot, there's no way to solve in terms of x or y because they're both squared. And if I take the square root, I'm not going to end up any better anyway. All right? Because I can't really take the square root, right? Because we have a positive and a negative. So when you have something like this, just solve it in terms of c. That's the one term you can solve it for. All right, so here we have another separable differential equation. This one's up here. This one has maybe a few more steps. So I'm just going to kind of go through it with you. We've got 2x times 1 plus y squared times e to the x squared is differentiable. It's a differential equation because it's got a derivative. The dy dx tells you it's differential. And it's separable because I can separate them using multiplication and division. They're not so stuck together that I can't get the x's from the y's. All right, so now we're going to multiply or divide. Actually multiply or divide, however you want to think of it. Either I'm multiplying by 1 over 1 plus y squared, or I'm dividing both sides by 1 plus y squared. All right, and that moves that y terms over. And then I have to multiply both sides by dx to move the dx's over. All right, so now I've got the y's with the dy's and the x's with the dx's. I do have a u to u substitution on the x squared. But I do have exactly what we need. We have the derivative of x squared there, so that completes the chain. Du is equal to 2x dx. So now on the left-hand side, we have 1 over 1 plus y squared dy. On the right, we have e to the u du. There's a simple integration here. We're using our rules for our inverse trig functions. This is arctan y plus a constant is equal to e to the u plus a constant. Substitute back. So now we have arctan y plus c equals e to the x squared plus c, and then just move the c's together. So arctan y equals e to the x squared plus c. You could also, so you can't really solve this for y. Well, no, excuse me. We can solve this for y because there's one other thing we can do. I think it's on the next page. We could take we could take tangent of both sides, couldn't we? I don't know if I did that on this or if I just left it like that. Nope, I continued. I thought I might have. So we could get rid of the arctan by taking the tangent of both sides, right? Tangent and arctan cancel each other out. We have y as an implicit function of x because y is not isolated. So that's why it's an implicit function. If we can isolate y, we can have it as an explicit function. And we can find y as an explicit function of x by taking the tangent of both sides. So if we take the tangent of both sides, tangent and arctan will cancel. I have y equals the tangent of e x squared plus c. Notice that you cannot factor out the constant c because the distribute property doesn't work with tangent. It's stuck there. The c was there first, right, before we took arctan. Before we took tangent, so it needs to stay as part of tangent. Right? Anything that's there before you use an operation has got to stay in that operation, unless there's a way to factor it out, and there is not. All right, so that's the end of this one. It's not really that difficult, except you had to remember that tan and arctan are inverses of one another. All right, here's another one. All right, so I have dy dx is equal to e to the negative y sine x. All right, so I'm going to take, get our x terms on one side and our y terms on the other side. So I'm going to actually simplify that first, just because I think it makes it nicer, that e to the negative y. So I'm going to rewrite that dy dx equals 1 over e to the y, right, because it's negative. E to the negative y is the same as 1 over e to the y. The negative exponent makes it the reciprocal. And then sine x. And the reason I like that is now I just multiply by e to the y. So I've got e to the y dy is going to equal sine x dx, right? I just multiplied one side by, this side I multiplied by e to the y. I'll put that in green. And this side, and of course dx. And this side I multiplied by e to the y dx. And the dx is canceled on one side, and the e to the y is canceled on the other side. All right, so now we can integrate both sides. So I have e to the y dy equals the integral of sine x dx. All right, so e to the y dy is just going to be e to the y. I'm going to put a constant with it. We'll combine the constants later. I think I even say combine the constants of integration. And then we're going to have, we take the integral of sine x dx. That's going to be negative cosine x plus c. And we can just combine those. So now I want to solve for y. I can isolate y here. I'm just going to combine the constants of integration. So I have e to the y equals negative cosine x plus, it's just one old c. We're going to take the natural log of both sides. So if you can undo an operation and to isolate y, then go ahead and undo it. In this case, I can undo the I can undo the exponentiation there by using natural log. So we have natural log e to the y equals natural log. I'm going to use the absolute value bars because cosine can be negative. Negative cosine, I can write that a little nicer too. Negative cosine x plus c, and c is going to be in the absolute value bars now too. All right, because it's got to be positive as well. So natural log and e cancel. I have y equals natural log, absolute value of negative cosine x plus c. I don't know if I continued this on the next page, but I managed to squeeze it in right there. All right, so we've got y isolated. And that's our differential equation. Right, so autonomous separable differential equations. A differential equation that is autonomous means that the derivative does not depend on the independent variable. For example, the equation below is an autonomous equation. Notice that there's no x involved. So dy dx means that the function of that y is defined for x. There is no x. Right? So we're going to look at some autonomous separable differential equations. So here you can still separate the y and bring it dx to the left. Bring dx to the right. Right? So here I continued on. So let me start with the green, and then I'll move to the yellow writing where I finished it off. So we have dy dx equals 3y. All right? So we can divide both sides by y. So now I've got and multiply both sides by dx. Right, so you've got the dx's will cancel. So now I've got dy over y equals 3 dx. All right, so now we integrate. Right, so we have 1 over blop to the first power. That's going to be natural log of blop. So natural log of y equals 3x plus c. And kind of like the opposite of the last problem, where we had to take the natural log of both sides, here we're going to exponentiate both sides. Right, so I'm just going to raise it to the e power, right? So kind of going off to the, we're working now from right to bottom to top. So if you go to the bottom there, I have e to the natural log of y equals e to the 3x. And there should actually be 3x plus c. I don't know where the c is in this one. 3x plus c. All right, maybe you got it erased. And so e and natural log are going to cancel. That frees y. So y is equal to e to the 3x plus c. So that's our solution. We exponentiate to isolate y when we have natural log of y. And we're going to see something else I could do to change that a little bit, that e to the y equals e to the 3x plus c. I could change that a little bit using well, I'll tell you what I can do. I can also rewrite this. So I can rewrite this as y equals e to the 3x times e to the c. And because now I'm just using the product rule for exponents. And then what's e to the c? Well, it's a constant, right? And I could rewrite that constant as a coefficient. So y equals a e to the 3x. But we're gonna take a look at that in dealing with writing exponential equations and how they are differential equations that we have solved for. Right? So let's look at the next one here. I only have a couple, I think, on these ones. All right, so we're going to have some exact and maybe that was the only one, I don't know. We have some exact value problems here as well. All right, so we have y prime is equal to 3 plus y. All right, so let's rewrite that. Y prime is dy dt or dy dx. In this case, I think it was a dy dt initially. So dy dt equals, and this one's an autonomous too. No, you don't see. That's why I don't know if it's an x or a t. I just have dy dt, so it must have started off as a t. And I don't know what it was because notice I have no x. All right, so dy dt equals 3 plus y. I cannot subtract the y, but I can separate the variables in the equation. The big thing I need to separate is I need that y with the other side. And the 3 is going to have to come along for the ride. Right? You can only use multiplication or division. So the 3 is coming along for the ride, and that's fine. I just have a little note there. Leibniz notation is the dy dx, dy dt. That allows us to have a separable differential equation. That's why that was so important. That was actually a very important invention, if you will, was to, instead of using y primes and things that I can't write as products and quotients, to change that to dy dx, it allows us to solve these differential equations. So it actually was a huge milestone. All right, so I'm going to move the dt to both sides, and I'm going to divide by 1 plus 3y. So I'm going to have dt in the numerator here over 3 plus y. So I'm going to divide by that. Equals, and then on the other, I'm going to do the same thing on the other side. I have 3 plus y, oops, except I left off the dy dt. dy dt equals 3 plus y, this is times here, times dt 3 plus y. All right, so these 3 plus y's are going to cancel. So I'm dividing both sides by 3 plus y, and I'm multiplying both sides by dt. And these dt's are going to cancel. So now I have 1 over 3 plus y dy equals dt. We're going to integrate that, right? And take the integral of both sides. 1 over 3 plus y, that's going to be natural log of 3 plus y, that is to the first power, is equal to, and this is going to be t. And I'll put the plus c here. And again, I can solve for that e. That y using e. Let me just see if I left room on the other page. Yeah, I did. All right, so I'm going to go to that one, and I'll go over this. So where we left off is we have natural log of 3 plus y equals t plus c. All right, we've taken the integral, and now we're going to exponentiate so we can get our y out of there. So we have e to the natural log of 3 plus y equals e to the t plus c. E and natural log cancel. I've got 3 plus y equals e to the t plus c. And now I'm actually kind of separating out this, that e to the t plus c, and rewriting that as e to the t and e to the c. So I've got y equals e to the t plus e to the c minus 3. All right, so that just becomes, and this was initial. This was an initial value problem. So I've got now that e to the c is just a constant. All right, we're going to use a to replace that constant, and that's our exponential equation. So this is the general solution right here. Let me mark that. This one right here is the general solution. Right? Because that, where c is, it can be rewritten as a coefficient. Now, this was a particular value, and the particular value that we were given y of 0 equals 1. So I'm going to plug in 0 for x and 1 for y, and we're going to solve for our a value. Right? So because now I don't have a c. Since c is an arbitrary constant, any function of c is an arbitrary constant. And so that we're letting a equals plus or minus e to the c. That is a constant. All right, so we've got 1 equals a to the e to the 0 power minus 3. All right, so now if I a to the e to the 0 power, that's just, if I add 3 to both sides, I got 4 equals a times e to the 0. E to the 0 is just 1, so 4 equals a. So the particular solution, I need to replace the a with 4, and so y equals 4e to the t minus 3. All right, so the product rule, add exponents to multiply like bases. That's what lets us change e to the, e to the t plus c into e to the t times e to the c, and then we can change e to the c to a. All right, so that's our particular solution. So since y is 1 when t equals 0, a has to equal 4. So I guess you probably never thought about our exponential equations as being rates like this, huh? And turning them into turning differential equations into them. All right, so I'm going to end this podcast, and I'm going to continue with slope fields in the next podcast. All right, and I'll have your closing at the very, very end of all of these podcasts, just one for the Friday. All right, bye.